All right, good morning. So welcome to session 2 of our wonderful study weekend. I have a couple of announcements. So just to remind you, if you need a quiet room to listen to the talks, there's a room upstairs where the talks are being streamed and you're welcome to go up there. We have 3 speakers this morning. Each of them has 30 minutes and Sam tells me he's been equipped with a bubble gun and authorized to deploy this should you go over time. So speakers, I will give you a 5-minute warning and then a 2-minute warning, trying to leave some time for questions. But yes, if we hit 30 minutes, Sam will appear with his bubble gun. Where are you, Sam, with the bubble gun? Do you want to give us a demonstration? Look at that, it's pretty exciting. Right, so we're going to kick off in our first talk of this session with Elspeth Garman. I think Elspeth needs no introduction to this community. So our doyenne of crystallography, Elspeth, would you like to come up?
Thank you very much indeed for the invitation to speak here. I have to admit that I first spoke at one of these 31 years ago, which is a bit scary because this doesn't work, Nick. Okay. Because nothing works, won't go up. Nothing will go. It worked a minute ago. I'm sorry, guys. What's happening? Nothing. This won't do anything.
Turn it off and on again.
It's a special thing. Oh yeah, great. That works now. Thank you very much.
There we go.
Yeah. Good. Okay. So yes, I first spoke 31 years ago when I was just pretty new to the subject, and this is the proceedings, which weren't in Acta D in those days. And the reason I'm telling you this is that my title was Problematic Data Collections, Give Up or Persist. And this, I sort of got a reputation for showing other people's rubbish data and having them sitting in the audience on the edge of their seats. And I do have a few PDBs which need attention, just to flag that up later. So if they're yours, I'm sorry, I didn't look up whose they were when I put them in. So what because I'm a hoarder, in my loft I found one of the overhead projector acetates that I used in that talk. I had my 18-month-old baby with me, and we discovered that the overhead projector didn't give any signal at all if it was coloured, and I had to spend the night in the bathroom going over them all in black pen because I'd colour-coded them. But it's relevant to this because it says, first, take heart. We've collected 450 data sets, which was a huge number in 5 years. 10% gave problems. With any luck, yours will not be one of the 10%. If the original data are untrustworthy, there's not much you can do later. And I think that's a really, really important message, which is still pertinent now. And so what I'd like you to do is to take heart about detecting and managing radiation damage, which is what I'm going to talk about. So the first systematic study of radiation damage was by, it was by, that's very strange. It's actually skipped one, never mind. But this is what I'm going to talk about. Yeah, okay. What are the symptoms? How can you spot it? What causes it? Very quickly on that, and some ways to avoid it, much more importantly, so that you don't have the problem in the first place. So the first systematic study of radiation damaging proteins was 1962 on myoglobin, and they did not even know what the sequence of myoglobin was at the time, but they came up with 3 really important results from that study, Colin Blake and David Phillips, that the damage was proportional to the dose, that each copper K alpha 8 keV photon absorbed by the crystal disrupts about 70 molecules and somewhat disorders another 90, so damages them but doesn't stop them diffracting. And the damage may be structurally specific, and we'll see that these were all prophetic. So we've had dose mentioned yesterday and this morning already. I'm just going to remind you what dose is, because it's one of my lifetime's efforts to get people to talk in terms of dose. So it's a very odd unit, really, because we can't actually measure it. We can only estimate it from the conditions of the experiment. It's the energy absorbed per unit mass. So it's joules, energy unit, over kilograms, which is amazingly unsuitable for protein crystals since they weigh micrograms or nanograms. It's a fundamental metric. We can plot damage against the dose, and it takes care of all the physics, as we'll see, but not the chemistry of what's going on in our crystals. So it's very much an estimate. So what sort of units are we talking about of these gray, GY, lowercase gray? Well, this hamster, and many of you have seen this hamster before, and I apologize on his behalf. If you give him 3 joules per kilogram of hamster, he will get internal organ failure and he will die. I haven't done the experiment. If you give a human being 2 gray a day for 30 days, they get 60 gray, and that's the maximum you can give a brain tumor in terms of radiotherapy. So what about our crystals? Well, it turns out that in our experiments, approximately we'll absorb 1 megagray, so that's 1,000,000 times 1 gray, obviously. That will be absorbed by a 100 micron cube metal-free crystal in normal operating conditions with a flux of about 10 to the 13 photons per second into a 100 by 100 beam. Now, what this means is that our crystals damage because they absorb the X-rays, and that spreads energy to ionize other parts of the crystal. There's an experimental dose limit which says that you shouldn't really zap your crystal more than 30 megagray. You can't expect it to give good results or even reliable results beyond absorbing 30 megagray. Note that that is 10 to the 7 times what we can give a hamster. Okay, so your crystals are really amazing at 100 Kelvin that they put up with this. That dose limit, though, of 30 megagray is reached in now in the new sources, 4th generation sources, can be reached in less than a second, and I'll show a plot of that later. And a normal beamline, certainly less than 10 seconds, you'll now reach that limit. And at free electron lasers with time with a pulsed beam, you'll reach that limit in less than 80 femtoseconds. So this is a limit. This is a hard limit, really, that biological material can sustain, can tolerate. So this is what happens at room temperature when you put a crystal on I-24. I love these pictures. The crystals were in a tray. They did get a data set from about 50 crystals by doing two images per position on the crystal here, and you see that that's breaking up while you're taking the images from there, and then the top's breaking up, and this is a direct result of radiation damage. And I love this as well, very sued, but they etched their beamline number onto a crystal just to show that the X-rays are not harmless. Okay, so what happens at room temperature is we start with a beautiful diffraction pattern, and we lose the high resolution high 2 theta reflections first. You can see now that we just don't have any data out here because of the radiation damage, and that happens pretty fast at room temperature. And if we look at a crystal that was irradiated for 2 milliseconds for successive images, and we averaged 240 of those, an experiment I was involved with at the ESRF, we can see the exponential decay of the intensity of the diffraction coming very neatly. It's not exactly exponential, and there are various models to reproduce this. This is at room temperature. So specific damage was first noted by John Helliwell from some experiments by Dagmar Ringer and Greg Petsko, and you see here difference density at a disulfide bond. So at room temperature, the disulfides will break. What's happening here is we're absorbing X-rays in a primary event, indirectly on the solvent, directly on a protein molecule, and the secondary results of this are going to spread through the crystal like a domino effect, and one absorbed 12 keV photon can produce 50 ionizations, sorry, 500, factor of 10, that's important. Factors of 10 are important, sorry. You see that what happens is at room temperature, we lose the we lose the intensity. This is I over sig I, and the resolution that we can actually process reduces. The arm merges go up, and the resolution of the data set will be worse. So what do? We cryo-cool our crystals down to 100 Kelvin. However, even at 100 Kelvin, we get damage effects. This was first logged beautifully by Teng and Moffat in 2000 also, Raymond Ravelli and Sean McSweeney, Martin Wyke et al. And Wim Burmeister all logged this. So I'm showing Teng and Moffat's results here. You can see what the crystal looked like after a while. The diffraction, the high resolution diffraction again has gone. The unit cell volume has gradually increased. This is very bad if you want to do a SAD experiment and keep your unit cell isomorphous. So even at cryo-cooled conditions, things are actually changing. The scaling B factors go up, and at some point they're not linear anymore. They're beautifully linear at the beginning. And then we see that the high resolution reflections, this is the intensity decay, dying off much faster than the low resolution reflections here. These are all the reflections with I over sig I greater than 20, and this is actually plotted against dose, which is terrific. I want to give a call out here to my dear friend and colleague, Raymond Ravelli, who died last year. He and Sean McSweeney plotted these from four different samples. And the worrying one that I haven't mentioned yet here is that the actual molecule appeared to rotate within the unit cell. This is very bad news because it means that the beginning of the data set might not be at the end of the data set, same as the end of the isomorphous with the end of the data set. This is probably a redefinition of the unit cell rather than all the molecules moving, but there's debate about exactly why you get this expansion. This rotation, and the unit cell volume increase is thought to be gas collecting at boundaries in the domain boundaries and dislocations in the crystal and causing the average unit cell volume to go up. As well as these effects in reciprocal space, we also see very nasty specific damage in, this is at 100K now, where it's very well characterized in a predictable hierarchy. And as I mentioned, at room temperature, we get disulfide bond breakage, but we also get reduction of all metallo centers. We think that nearly all of the PDB metallo enzymes are actually in a reduced state. This shows lysozyme. This is a Raymond Ravelli picture, and you see the four lysozyme disulfides here. The red density is difference density between the first and fourth data set, and you can see that in some places these disulfide breaks like this, and the sulfurs go to specific positions, but in other places, especially near solvent boundaries, the sulfur molecule doesn't go to a sulfur atom doesn't go to a specific place. We also see worryingly aspen glue decarboxylation at 100K, and we see cleavage of the SC bond in methionine as well. If you've got anything covalently bound that's heavy, like bromine, iodine, and mercury, then you also see those rupturing as well. Okay, so the other thing we see in our PDBs is that the atomic B factors increase with those quite significantly, and we can actually use that to detect radiation damage in the protein data bank, as I'll come to. So in summary of this section of the talk, we've got global radiation damage, so-called in reciprocal space, with all of these effects that I've talked about. And then we've got specific radiation damage, chemical changes here. It was thought that you lost the OH off tyrosine, but that's actually a movement of the tyrosine rather than losing it. So what causes this, these effects? And this is going to be very cut short from my usual diatribe about this. We've got two things going on. We've got diffraction, which is elastic scattering, and we've got absorption, which is energy loss. And the absorption is what we depend on when we have an X-ray at the hospital. If we've broken anything, I hope you haven't, but if you have, you can see this because your bones your bones absorb more X-rays because they're denser than your flesh does. So you get a negative image of your break. So this is a fact of physics. We just can't do anything about the fact that any matter in the X-ray beam is going to absorb as well as elastically scatter the X-rays. It's interesting that 90% of the beam goes through the crystal. It doesn't interact at all on a 100 micron crystal at 12 keV. This means you have to have a backstop, otherwise your detector gets fried. But that's a different talk. Okay, so what are the processes that are involved in the absorption? There's two of them. One of them is called Compton scattering. That's inelastic scattering, where the X-ray comes in, loses some energy to an atomic electron, which is ejected without much energy, and it goes out at a longer wavelength, lower energy. That's only 8% of what happens. Sadly, diffraction is only 8% of what happens at 12.4 keV. For a 100 micron crystal as well. The real problem we have is the photoelectric absorption, where an inner shell, highest cross section is for an inner shell electron to be ejected, and it goes out with almost the same energy as the incoming X-ray minus the binding energy of it around the atom, and as I said, has enough energy to ionize 500 other atoms. So that's really what's harming us, and I'll come back to what we can do about that in a minute. So how are you going to spot during your experiment that you how are you going to spot radiation damage during your experiment? So we're already halfway through, Arwen, so don't panic. Yeah. Okay. So during the experiment, what can we do? Well, the best thing, as you're actually taking data, you can keep an eye on this plot, which is a per image analysis plot. And the three things plotted on here, the blue spots, we've seen a lot of these already in the last 2 days, are the Bragg spots. And what you notice about this one is that I had the same orientation of the crystal. I had a lot more spots at the beginning than I've got by the end. I have to say that Ed Lowe gave me this, and he had a lot of trouble finding anything that showed these pathologies, because he's very good at collecting data that is not radiation damaged. But you can see here that you can see them dropping off. The yellow ones are the number of spots above a certain sigma, I over sigma. And you can see they're also dropping off. And if you look at the resolution here, that's harder to see, but it's also starting to go off. So keep an eye on this. And if you see this happening, then your crystal should be taken off and you should put a new one on. If we look at what the auto-processing gave for this same case, we see that the R merge, which is the internal quality indicator of the agreement of the images with one another, goes up off the roof here at around the place where the resolution started to get worse. And we also see this very characteristic U shape in the scaling B factors. And that is because the software is doing its best to try and get a scale which matches most of the data. So it minimizes the central bit, and then the two edges end up with higher scaling factors to try and make them agree. Whereas you'd have thought it would go like that, but it doesn't. It tries to make most of it agree as best it can. So that's what this U shape comes along. What can we do to actually plot it if we're looking for radiation damage? Well, we can plot the intensity of successive data sets, which is what's up here, over the intensity of the first data set. We can plot the scaling B factors with the first scaling B factor subtracted off, which is why it starts at 0. And this is called the coefficient of sensitivity, the slope of this SAD, or the Chi-Diedrichs indicator, where you look at the internal merging R between images which have the same reflection on, and you plot along here the difference in their dose. And if you had no damage, you shouldn't see any difference as you go through the data set, but if you've got damage, that will go up. So that's during the experiment and when you look at your processing. What about during the refinement? Well, as I mentioned, the atomic B factors can rise quite significantly with radiation damage. And you can, at the end of your refinement, you can get a radiation damage index by using the CCP4 program RABDAM, written by Catherine Shelley, who's now with David Baker in Seattle, University of Washington. My student Marcus Gerstel developed this B damage indicator, which involves deconvoluting the packing density from the B factor, from the atomic B factor, to give a residual, which we call B damage, because clearly atoms on the outside have more freedom of movement and will naturally have a higher B factor than atoms in the middle. So you get a number, and you can see here that this has highlighted some bad places in this acetylcholinesterase, molecule, and it highlights where the damage, where the B factors are higher than they ought to be or higher than the surrounding atoms. From this, Catherine derived a B net, which we then allocated to 93,000 of the PDB, 100K PDB, better than 3 angstroms in the data bank. And these are 2 of the ones that had very high B net. And sure enough, when you go and look at the difference density, is anyone going to admit that these are theirs? Okay. So you can see that the decarboxylation I mentioned has happened here. Right, I need to hurry up. So ways to avoid it. The first and most important way is to do a sacrificial crystal to characterize the damage rate by, for instance, going around 360 degrees as long as the crystal lasts and just plotting the total intensity and seeing how long you've got before you damage the crystal to below the absolute worst you should take it is to 0.7 of its original intensity. Sorry, my point. Oh, there it is. There it is. 0.7 there. That's the actual, the absolute lowest you should take it. The second thing you should do is estimate the dose and keep it low. We need to find the dose. We need information on the beam and the crystal. Many of you have seen me talking about this before. So we need all this information about the crystal to work out the absorption coefficients, how many X-rays it's going to absorb. We also need to know what's in the solvent, because anything heavy in the solvent can cause trouble by absorbing more X-rays. We need to know about the beam, and we need to know the flux of the beam, and we need to know the size and profile of the beam. And all of this goes into the estimation of the dose. So all of this feeds into the green here, which is the dose. So it's a lot of information we need in order to estimate it. But there's a program that does all this for you called RADDOS 3D, written over the last 10 years by my group. And the good news of the day, I'm not going to go through all the things it can do, is that thanks to Nick, Marcus and Graham, this raddo.se, which is hosted in Sweden, which is why it's SE, is working again. And you can go on here and you can fill in numbers and play with this and actually try. And it hadn't been working for a while. But the even better news is that we're about to actually release a RADDOS GUI, which, because people like GUIs, written by Josh Dickerson, now working with Chris Russo in Cambridge at MRC LMB. And that will also, we're writing about to submit the paper about that. So some beamlines have actually put RADDOS 3D underneath to allow collection by dose, not time. This is from SSRL. All the beamlines there run blue ice, and blue ice has incorporated it in. So here it predicts this is a room temperature collection. 0.38 of a megagray is the dose limit. And we're predicted that it's going to give a megagray. So it'll be fried, basically, that crystal. But IO4 has also implemented this, I'm really happy to say. And thanks to Ralph Flagg for this slide. And this shows the take-up of collection by dose rather than by time. And you can see that people are persuadable, because the red is almost, there's only a few dinosaurs here now collecting by time. Thank you. So this is what you would fill in on IO4. You've got to avoid the temptation to increase the exposure time or the dose just to see if you get more spots. And the rule of thumb from Ed Lowe, my long-term colleague, is that 10 to 15 megagray is absolute maximum over 360 to 720. But if you've got a high resolution diffracting crystal, then 7 megagray should be an absolute limit. If this is all too much for you and you can't really cope with it, you can always go on to James Holton's quick calculator lifetime. This is a much more simplistic approach than RADDOS 3D, but you can put the numbers in here and play. The IO4 actually flashes up red if you try and take a data collection that's going to fry the crystal, which is terrific. So what are the time limits to the dose? What time to the dose limits do you actually have fourth generation synchrotrons. And this, the amount of work in getting all this information is belied by the simplicity of the plot. But you see here, this is the time to 30 megagray, which is a experimental dose limit, and the time to 0.4 megagray, which is the rough room temperature dose limit. And you can see here, this is the dose rate that's delivered by these beams, and this is the time you've got in seconds, and it's plummeting. I mean, here we are at I29 at less than at 10 milliseconds. So this is something to worry about. Now, the third thing you can do is spread the dose. So if you've got a crystal that's bigger than the beam, you can either fry it by just rotating it like this in the middle, and then you see the fried egg effect here, which is more than 30 megagray in the middle. Or you can do Newton's cradle if it's long and thin and move it, do 10 degrees at each place. Or you can do the helical one, and that's harder for me to do. Right, like this. With it in order to spread the dose. What you want to do is avoid the dose going above any of the limits and use all the volume of the crystal if you possibly can. So this one is quite funny because you offset the center of the crystal and you get a donut shape. And if you can offset the center and do this, then you really spread the dose for the same number. The fourth thing you can do is back soak to remove non-specifically bound heavy atoms, and particularly bad in this scenario is cacodylate. The tip is to try and avoid using it because the absorption cross-section for the photoelectric effect that I mentioned is actually very high. So if we look at the absorption cross-sections, and the size of these atoms is proportional to the size of the cross-section at 13.1 keV incident X-ray energy. And if you have a selenomethionine derivative and you wonder why it damages much faster than your native, the reason is that is the selenium. 2 minutes. Okay, thank you. So the fifth thing you can do, and this is where the beamline scientists will probably shoot me, but you can use a top hat beam instead of a Gaussian beam. So if you look at these beam cross sections here, this is a beautiful Gaussian from I24. Thank you, Danny and Robin. And if we look at the dose profile, the dose that's actually, this is a great pointer, but sometimes it doesn't like me. Okay, the top one, okay. The dose in megagray goes up to 3 at red. If we have a top hat beam, thank you, Gleb Barankoff and Thomas Schneider, on P14 at Petra, then you can see that you're irradiating the crystal evenly. So even if you're damaging it, you're damaging everything at the same rate. So all the disulfides will be breaking at the same rate rather than having differential damage going through. This use of a Gaussian beam can give some very odd results, and I haven't got time to go into this, but it's in this PNAS paper. It seemed to say that the disulfide bond electron density actually recovered with time, and it's because the tails of the beam were giving us that diffraction. The middle of the beam had burned the crystals out. So the other thing, and I'm just coming to my summary, Owen. Yeah, okay. You can exclude damaged images. So this is an example which Catherine Shelley actually showed last year at the CC4 study weekend from a long time ago from data I collected at SSRL in the late 90s. And this was absolutely stunned me when I took 33 images out of the end of the very high resolution data set, high 2 that was. Ligand that I had bound in my Salmonella typhimurium neuraminidase crystal sort of disintegrated. So if you think you've got bad images, just cut them out. You probably don't need them to get the electron density. So in summary, I've covered low dose, fine slicing, high multiplicity strategy, without actually saying that, but that was underlying. Expose a sacrificial crystal, estimate your dose, spread the dose, back soak, use a top hat beam. Don't be afraid to merge data from different isomorphous crystals, which all had lower doses. We've got fantastic software that can do that now. I haven't mentioned high energy X-ray data collection. That has been mentioned twice yesterday. There is a sweet plot around 26 keV that we found from simulating the properties of a cadmium telluride detector, and that's been verified by Selena Storm and Danny Axford and Robin Owen. So the main thing is that you can't estimate the dose unless you know how many X-rays are coming down the beamline. So you should ask your beamline scientist, what is the flux today, not 5 years ago, today, and with this slit size at this beam energy, and what's the full width half maximum in X and Y. And given that, you can actually estimate the dose and then be within the limits of what your crystal will tolerate. I want to thank my group. I'm now retired, as you can see, many thanks to all my past research group and collaborators. They made a huge contribution to very non-sexy research on radiation damage, I thank them very, very much. And this was rather a lot of material that I delivered rather fast, so please ask me some questions. There's some further reading there if you're interested in this subject of radiation damage, rather than just thinking, oh, it's a problem that you can't deal with. You can deal with it, and you can avoid it if you want. And those are all my graduate students. And I wanted to point out that it's very good to learn to code, because you can go and get very high paying jobs at Facebook and Spotify. And I sometimes wonder what Raddos 3D has given the world, actually. Okay. Yeah.
Elspeth is perfectly on time. We have a couple of minutes for questions. So I'll take questions first from the room. And Sam, I think you're looking at the Slack chat to see if there's anything there. So questions for Elspeth. Helen.
Can you quickly explain when you had the that figure from Ed with the reduction in the spots over image number? Can you explain why there are two peaks where the spots are in particular high?
Yeah, good question. It's because if I'm a crystal, and if you notice I'm a bit thinner that way than that way, okay? So if that Arwen's the X-ray beam, right, I'm going to get lots of spots when she goes through that way, right? And then I turn 90 degrees and there's fewer spots, and then I turn again and there's more spots, and then I turn again and there's, does that make sense? Yeah. Brilliant. So yeah, so it's a volume, it's the volume of crystal that you're going through.
So should PDB validation include radiation damage metrics, and if so, which ones?
Yeah, very, very good question. I would love the PDB to take RabDam on, and I've been trying to push that. But as you know, it's quite hard to change the validation protocols of the PDB. But I mean, I think that everybody can have a look before they submit their PDB just by running RabDam on the CCP4 suite, and it'll flag up the places where BNet is, well, it'll give it one overall index. And if it's more than 3, I would worry. I would go around and look at all your damaged glutamates and aspartates. So yes, that would be great. I mean, you know, 2 ambitions in my life: to get Raddos actually underneath the beamlines so that you can collect via dose and get that into the PDB validation. The thing is, we tried with room temperature structures, but it doesn't work as robustly for room temperature structures. There aren't as many for us to get the statistics out on, whereas there were 93,000 that we could run this on. It took quite a lot of computer time.
Last question from up here.
Martin Marie, Southampton. Please, can I ask you, I was wondering, do you know that those data collection strategies that you present us are available at the controlling software, the beam lines? Because I know usually there is a helical scan. There it is, but I like the last option that you showed us, but I'm not aware it's there.
You would have to you'd have to manually displace it from the center of rotation, because all the software is trying to put the crystal in the middle, you know, at the center of rotation, because that's the normal thing to do. So I think you'd have to manually displace it, but I don't know about the Garman beamlines. I know that helical is available on I-24. I don't know about on all the others. Perhaps someone from Garman, Graham will answer that in the next talk.
I think it's available on almost all of them, the helical ones, and there's wedge and helical varieties. So you can either like do a wedge move, or you can do a continuous helix.
Yeah, so Newton's cradle or spiral staircase. Yeah.
All right, I'm afraid we have to move on, but Elspeth is here for the whole rest of the study weekend, so you can catch her in the break times if you have more questions.